At the edge of Webb's vision, the young universe should have been faint, simple, and slow to take shape. Instead, the telescope found early galaxies already shining with unexpected strength, carrying signs of rapid star formation, chemical enrichment, and perhaps even hidden black holes feeding in the dark. These are not loud science fiction claims, but quiet measurements from ancient infrared light, and they have made cosmic dawn far less simple than it once seemed. If calm, thoughtful journeys like this help bring a little wonder into the day, please like, subscribe, and share this video so Calm Space Science can continue creating careful science stories for peaceful viewing. Thank you for spending your time here with us. In the comments, tell us where in the world you're watching or listening from, what time it is there, and whether this is part of work, study, rest, or sleep. Now the oldest light begins to tell its story. The James Webb Space Telescope begins this story not as a symbol of certainty, but as an instrument built to reach a difficult kind of evidence. Its mirror is wide enough to collect extremely faint light, its detectors are tuned for infrared wavelengths, and its orbit keeps it in a stable, cold observing environment far from the heat and glare of Earth. These details matter because the oldest galaxies do not arrive in modern telescopes as clear, ordinary pictures. They arrive as weak traces of light that have crossed nearly the entire observable history of the universe. By the time that light reaches the telescope, it has been dimmed by distance, stretched by expansion, and shifted out of the visible range. Webb was designed for that exact problem. It does not simply take sharper photographs of space. It reads the long travelling light that has survived from the earliest visible stages of cosmic history, and in doing so it turns distance into a record of time. The basic idea is simple. Light needs time to travel. The farther away an object is, the longer its light has been on the way. Nearby objects are seen almost as they are now, while distant galaxies are seen as they were when their light began its journey. At the scale of the universe, this delay becomes enormous. A galaxy billions of light-years away is not only far across space, it is also far back in time. Its image is not a current report, but an old message preserved in motion. This is why deep astronomy has a strange double meaning. Looking outward also means looking backward, and a telescope aimed at the most distant galaxies is effectively reading earlier pages of the universe. Webb was built to read pages that had remained almost closed. Before it, telescopes such as Hubble had already shown that the deep sky was crowded with galaxies, many of them far older than anything visible to unaided eyes. But the first galaxies remained difficult to study because their light had been altered by the expansion of space itself. As space expands, light travelling through it is stretched into longer wavelengths. Light that may have left a young galaxy as ultraviolet or visible radiation can arrive today as infrared light, a form of light beyond human vision. This stretching is not a small detail. It is the reason Webb had to be an infrared telescope. Without infrared sensitivity, much of the early universe would not simply look faint. It would be shifted into a range that the telescope could not properly see. Webb's large mirror gathers more of that faint radiation, and its cold instruments reduce the heat that would otherwise interfere with the signal. The telescope's sunshield is therefore not just an engineering feature, it is part of the scientific method. By keeping the observatory cold, it allows ancient infrared light to stand out from the instrument's own warmth. That cold precision gives astronomers a clearer chance to separate a real galaxy from background noise and to measure the light in enough detail to learn what kind of object produced it. This is why Webb's first deep observations carried so much expectation. They were not only beautiful images, they were tests of a long-standing picture of how structure began. The earliest universe, after the first hot phase, contained mostly hydrogen and helium, with very little of the heavier material later made inside stars. It had no mature spiral galaxies, no long-lived stellar systems like the Milky Way, and no chemical richness comparable to the later cosmos. Matter had to gather under gravity, gas had to cool, stars had to ignite, galaxies had to assemble from smaller beginnings. That process was expected to take time, and the first visible galaxies were expected to be small, faint, and still in the early stages of growth. Webb was sent, in part, to test that expectation directly. It would look for the earliest detectable galaxies and help determine whether the first stages of cosmic structure match the models. The first important point is that Webb does not see the beginning itself. The first moments after the Big Bang remain hidden behind conditions that no ordinary light can cross. The telescope instead studies the era after the universe had cooled enough for light to travel freely, and after gravity had begun drawing matter into the first luminous structures. This period is often called cosmic dawn, because it marks the rise of the first stars and galaxies. The phrase is useful, but the real process was not simple or uniform. Different regions likely evolved at different rates. Some areas may have formed stars earlier than others. Some clouds of gas may have collapsed more efficiently. Some early galaxies may have been unusually bright for reasons that were not yet understood. Webb's purpose was to replace broad expectation with direct evidence. Its images and spectra could show how many early galaxies existed, how luminous they were, how compact they appeared, and what their light suggested about their stars, gas, and chemistry. The method begins with observation, but it does not end with a picture. A distant smudge in a Webb image is only the first clue. Astronomers then measure how its light changes across different wavelengths. They compare its colours, search for sharp breaks in the spectrum, and, when possible, use spectroscopy to spread its light into a detailed pattern. This pattern can reveal how far the light has been stretched and whether the object truly belongs to the early universe. It can also show whether the light is mostly coming from stars, glowing gas, or a feeding black hole. These distinctions are essential because the early universe is not easy to interpret. A dusty galaxy closer to Earth can appear red. A young galaxy with intense emission from gas can look brighter than its stars alone would allow. A black hole feeding at the centre of a small galaxy can produce enough light to mimic a far larger stellar population. Webb gives astronomers the tools to investigate these possibilities, but the work remains careful and slow. Every extreme claim has to survive the possibility of misidentification. That caution is part of why the telescope's early results became so important. The surprise was not based on a single image or one uncertain object. Webb began finding many candidates for very early galaxies, and some were brighter than expected. As follow-up observations improved, not every early claim remained as strong as it first appeared. Some masses were revised downward, some objects became less unusual after better data, yet the overall pattern did not disappear. The early universe still seemed more active than many models had predicted. Webb was not merely adding decoration to an old story. It was showing that the first chapters may have been more crowded, more luminous, and more efficient at building structure than expected. This is the quiet tension at the centre of the subject. The telescope was built to confirm and refine the known timeline, but its strongest observations have also exposed places where that timeline may need adjustment. In that sense, Webb's power is not only its ability to see faint things, it is its ability to make old assumptions measurable. Before Webb, many details of cosmic dawn were hidden behind distance and technical limits. Models could estimate what should happen, but direct tests were scarce. After Webb, the early universe has become a field of specific objects with measured light, candidate distances, chemical clues, and structural hints. Each faint red source is no longer only a point on an image. It becomes a question about time. How much matter had already gathered there? how rapidly stars were forming, whether heavy elements had already been produced, whether a black hole was adding to the glow, whether nearby gas had been cleared enough for light to escape. The answers do not all point in one simple direction yet, but they have made one thing clear. The early universe was not empty, slow, or easy to summarize. It was already doing complex work at a very young age. Webb stands at the beginning of this new examination, gathering light that began its journey before Earth existed, before the Sun existed, and before most of the familiar universe had taken shape. That light reaches the telescope not as a finished explanation, but as evidence that has to be separated, measured, and interpreted. The calm surface of a deep field image hides an immense amount of information. Every faint red mark may be a young galaxy, a compact star-forming region, a dusty imposter, or the glow around a black hole. The task is to sort those possibilities without forcing the data to fit a preferred story. This is why the discoveries feel troubling in the scientific sense. They do not destroy the idea of the Big Bang, and they do not make cosmology collapse. They do something more precise and more useful. They show that the earliest visible galaxies may have formed stars, gathered mass, enriched their gas, and lit their surroundings faster than expected. Webb has opened the deep past enough for the problem to become visible, and the first lesson is that the edge of observation is not quiet. It is filled with signals from a young universe that was already more active than the simplest version of the story had allowed. The phrase edge of the universe can easily suggest a boundary, but in astronomy it means something more careful. Webb is not looking toward a physical rim where space stops. There is no known wall at the outer limit of the cosmos, and no evidence that a spacecraft moving far enough would reach a final surface. The edge involved in Webb's deepest observations is an observational edge. It is the farthest region from which light has had enough time to reach the part of the universe now visible from Earth. That difference is important because it changes the meaning of every distant galaxy in a Webb image. The telescope is not finding objects lined up along the end of space. It is finding the oldest accessible light, arriving from places that were already far away when their light began travelling, and have been carried farther still by cosmic expansion. The limit belongs to sight, not necessarily to existence. The universe may extend far beyond what any telescope can observe, but information from those farther regions has not had time to arrive. This visible portion is called the observable universe, and it is the full region from which light or any other signal could, in principle, have reached Earth since the beginning of cosmic time. Its size is set by three facts working together: the age of the universe, the speed of light, and the expansion of space. The age sets how long light has been able to travel. The speed of light sets the fastest possible rate at which information can move. Expansion changes the distance scale while the light is on its way. These facts make the observable universe larger and stranger than a simple travel time calculation would suggest. A galaxy whose light has travelled for more than 13 billion years is not merely 13 billion light-years away in the ordinary sense, because the space between that galaxy and the Milky Way has expanded during the journey. The light records a young object from long ago, while the object's present location, if it still exists in recognizable form, is far beyond the distance implied by the travel time alone. This is one reason the earliest galaxies can feel conceptually difficult. Their light is old, their original state is ancient, and their present form is unavailable. Webb receives the past, not the current condition. The observable edge also means that astronomy is not arranged around Earth in any special physical sense. Every observer in the universe has a visible region centered on their own location, because light reaches each observer from a different set of distances and directions. Earth sits at the center of its own observable universe only because observation is being made from Earth and from telescopes near it. This does not make Earth the center of all space, It means the visible horizon follows the observer. The same idea would apply from a distant galaxy. Observers there would see their own cosmic horizon, with some regions overlapping ours and others forever hidden from it. This point matters because Webb's deepest view can seem like a look at an outer shell surrounding humanity, when it is really a look toward a time boundary built into the history of light. The farther the telescope looks, the closer it comes to periods when galaxies were first forming. At some point, ordinary starlight and galaxy light end because no stars or galaxies had yet appeared. Beyond that lies an earlier glow called the cosmic microwave background, the cooled remnant of the time when the universe first became transparent to light. Webb is not designed primarily to study that glow. Its work begins later, in the era when matter had started to form the first stars and galaxies. This gives cosmic dawn its importance. It sits between the smooth early universe revealed by the microwave background and the structured universe filled with galaxies seen at later times. It is the transition from an almost featureless beginning to a universe with luminous objects, and that transition is exactly where Webb has found unexpected activity. The edge Webb studies is therefore not one single distance or one clean surface. It is a moving scientific frontier made of faint detections, uncertain candidates, and confirmed objects at different redshifts. Each improvement in instrument sensitivity and data analysis can move the practical edge farther back. Before Webb, many of the earliest galaxies were predicted rather than measured in detail. Hubble could reach impressively deep, but its sensitivity to the most stretched infrared light was limited. Webb changes the frontier because it can observe wavelengths where the oldest galaxy light arrives. In practical terms, this means the edge is not only defined by the universe, it is also defined by technology. A galaxy may have been sending light toward Earth for billions of years, but it becomes part of astronomy only when an instrument can detect it and measure it reliably. Webb's deep observations have widened the known sample of galaxies from the first several 100 million years, turning the edge from a sparse set of hints into a richer field of evidence. Yet this gain in reach brings a new kind of caution. The farther back the telescope looks, the more difficult each measurement becomes. Early galaxies are faint not only because they are distant, but because their light is spread out by expansion and often mixed with other sources along the line of sight. A small error in identifying a signal can move an object to the wrong era. A red colour can suggest extreme distance, but redness can also come from dust in a nearer galaxy. A compact bright source can suggest a large number of stars, but it can also be intensified by gas emission or by a feeding black hole. The observational edge is therefore a place where certainty has to be earned slowly. Candidates appear first, then stronger measurements test them. Some survive and become confirmed members of the early universe. Others are revised, reclassified, or removed from the most extreme category. This does not weaken the science. It is how the science protects itself from overstatement. What remains after that process is more important than the first headline. Webb's troubling result is not that every distant candidate is exactly as massive or extreme as initial estimates suggested. It is that even after careful checks, the early universe contains more bright and developed galaxies than expected. The edge keeps producing objects that cannot be dismissed as simple mistakes. The region once expected to contain mostly faint, primitive systems now shows signs of intense star formation, compact structure, and in some cases chemical enrichment. That does not mean the entire model of cosmic history is wrong. It means the period near the visible boundary is more active and less gradual than many simplified descriptions had implied. The physical universe still follows gravity, expansion, cooling, star formation, and feedback. The question is how those processes combined so efficiently in the first short interval of cosmic time. This makes the observable edge a test of growth. Nearer galaxies show what the universe became after long development. The farthest galaxies show how quickly that development began. If Webb finds a galaxy only a few 100 million years after the Big Bang, then every star contributing to its light must have formed earlier still. Any heavy elements in its gas require stars that had already lived and died. Any central black hole bright enough to affect the measurements must have grown from an even earlier seed. Each observation near the edge pushes the required beginning farther back into the dark interval before direct galaxy detections become easy. In this way, the edge is not only a limit of what can be seen, it is a pressure point on the timeline. It asks how much structure can fit into the available time without breaking known physics or requiring new assumptions. Webb has made that question sharper because it can see enough early objects for patterns to emerge. A single remote galaxy might be unusual. A growing population begins to describe conditions. If many young galaxies are bright, compact, and efficient at making stars, then the early universe may have favoured rapid growth in ways that later galaxies no longer reveal clearly. Gas may have been denser, star formation may have been more concentrated. The first stellar populations may have produced more light per unit of mass. Early black holes may have contributed more often than expected. Dark matter halos may have provided deeper gathering places sooner than some models predicted. None of these possibilities requires abandoning scientific caution. They require better measurements and a willingness to let the visible edge revise the details of the story. Webb's view of that edge is therefore troubling in a disciplined way. It does not point to a cosmic boundary where explanation fails. It points to a boundary where observation is finally strong enough to expose unfinished parts of the model. The farthest light shows that the young universe had already begun organizing itself with surprising speed. The next task is to understand how distance, time, and expansion turn that light into a measurable age. Because without that measurement, the edge would remain only a faint red glow, rather than a dated record of cosmic dawn. The measurement that gives the observable edge its timestamp is redshift. Without it, the farthest galaxies would be only faint red marks in an image, interesting but not securely placed in cosmic history. With it, their light becomes a record that can be dated. Redshift measures how much the wavelength of light has been stretched while travelling through expanding space. A wavelength is the distance from one crest of a light wave to the next. Shorter wavelengths correspond to bluer or more energetic light, while longer wavelengths correspond to redder light and, beyond visible red, infrared light. When astronomers say that a galaxy has a high redshift, they mean that the light from that galaxy has been stretched by a large amount before reaching the telescope. In a universe that is expanding, this stretching is expected. The space between distant galaxies increases while the light is still crossing it, and the light is carried along with that changing scale. The more expansion the light experiences during its journey, the more its wavelengths lengthen. This is why redshift is connected to distance and time. Light from a nearby galaxy has crossed a smaller amount of expanding space, so its wavelengths are changed only modestly. Light from a galaxy near cosmic dawn has travelled across most of observable history, so the stretching is much stronger. Webb was designed around this fact. The earlier stars and galaxies may have emitted much of their light in ultraviolet and visible wavelengths, but by the time that light arrives near Earth, it has been shifted into infrared. A telescope that cannot observe the right infrared wavelengths would miss much of the signal or measure it poorly. Webb's infrared instruments are therefore not an optional improvement over earlier telescopes. They're essential for studying the first galaxies directly. Redshift also explains why the most distant galaxies often appear very red in Webb images. The redness does not necessarily mean the galaxies themselves were red in the ordinary sense when the light left them. Many early galaxies were likely dominated by hot, young stars that emitted strong ultraviolet light. The red appearance is produced by the long journey through expanding space. The universe has changed the light during travel. moving it into longer wavelengths before it reaches the detector. This distinction matters because a colour in an image is not the same as a simple photograph of the object's original colour. It is a measured consequence of distance, time, expansion, and the telescope's filters. Astronomers begin by observing an object through several filters, each sensitive to a different range of wavelengths. If a galaxy appears in longer wavelength filters but disappears in shorter wavelength ones, that sudden drop can suggest a very high redshift. The drop occurs because hydrogen gas in and around the early galaxy absorbs light below a certain wavelength. Expansion moves that break to longer wavelengths. By locating where the break appears, astronomers can estimate how strongly the light has been stretched. This method is useful because it allows large numbers of possible early galaxies to be found quickly. It is also uncertain because several different physical situations can produce similar colours. A dusty galaxy at a lower redshift may appear red. A galaxy with unusually strong gas emission may appear brighter in one filter than expected. A compact active black hole can add light that changes the apparent shape of the spectrum. This is why redshift estimates from images are treated as candidates rather than final proof. They guide follow-up work, but they do not end the argument. The stronger method is spectroscopy. Instead of measuring the light in broad filters, spectroscopy spreads it into a detailed spectrum. In that spectrum, astronomers search for specific features that can be compared with known patterns from atoms and molecules. Hydrogen, oxygen, carbon, and other elements produce or absorb light at characteristic wavelengths. These features act as fixed reference points. If the same pattern appears shifted to longer wavelengths in a distant galaxy, astronomers can calculate the redshift precisely. The result is not only a better distance estimate, it also becomes a stronger age estimate. Because cosmological models connect redshift with the time at which the light was emitted. A galaxy at a redshift above 10 is being seen when the universe was only a small fraction of its present age. A galaxy at still higher redshift belongs even closer to cosmic dawn. These numbers are not casual labels. They are the coordinates of early cosmic history. They say where the object sits in the timeline accessible to observation. The reason this becomes troubling is that redshift limits how much time was available before the galaxy emitted the light now being measured. If a galaxy is confirmed at a very high redshift, then it cannot be moved to a later, more comfortable era. Its stars, gas, and possible black hole must already have existed at that early time. The measurement turns a surprising appearance into a chronological problem. A bright galaxy at moderate distance may be impressive but not difficult to explain. A bright galaxy at very high redshift is different because the universe had less time to build it. Redshift is therefore the gatekeeper of the whole question. It tells astronomers whether an object is merely unusual or whether it belongs to a period when such development was not expected. This is why so much attention falls on confirmed redshifts rather than early image-based claims. The history of deep galaxy research contains many objects that looked extreme at first and became less extreme after better measurements. That process is healthy. It removes weaker claims and leaves a smaller set of stronger ones. Webb's most important contribution is that a growing number of early galaxies have survived this process. Their redshifts have been measured in enough detail to place them in the first several 100 million years of cosmic history. Once the redshift is secure, the remaining questions become more physical. How many stars are needed to produce the observed light? How rapidly could those stars have formed? How much gas was present? How compact was the source? Whether heavy elements had already appeared? Whether an active black hole contributed to the brightness? Each question depends on the first one being answered correctly. The object must be placed in time before its development can be judged. Redshift also carries a second, quieter implication. It means that the early universe is not being observed all at once in a single frozen layer. Galaxies at different redshifts show different moments in the unfolding of structure. A galaxy at one high redshift may be seen a little later than another at a higher redshift, even if both belong to cosmic dawn. By comparing many objects across these redshifts, astronomers can begin to reconstruct how quickly the population changed. If galaxies become dramatically more common or brighter over a short redshift interval, then star formation may have accelerated rapidly. If heavy elements appear in galaxies at redshifts where little enrichment was expected, then earlier generations of stars must have already completed their lives. If compact bright sources are common at very high redshift, then the first galaxies may have formed in dense environments with unusually efficient gas collapse. Redshift turns scattered detections into a sequence. The sequence is still incomplete, but is already more active than many expectations allowed. The most careful interpretation is not that redshift has revealed an impossible universe. It has revealed a young universe with demanding timing. The standard framework still explains why light stretches, why distant objects are seen in the past, and why early structure grows from small density differences under gravity. The pressure comes from the pace. Webb is finding luminous systems so early that the usual rates of star formation, chemical enrichment, and black hole growth may need revision. Some of the tension may ease as measurements improve. Some galaxies may turn out to be less massive than they first seemed. Some brightness may come from gas or black holes rather than stars alone. But redshift prevents the entire problem from being moved away. For the confirmed objects, the early dates are real. The universe was already making detectable galaxies when only a short interval had passed since its hot beginning. This is the foundation beneath the later surprises: brightness, mass, chemistry, compactness, and reionization all become meaningful only after redshift places the source in time. Webb's deep images may draw attention because they show the crowded darkness of the distant sky. But the deeper discovery comes from measuring how that light has been stretched. Redshift is the clock that gives the image its age, and once the clock is read, the early universe appears less gradual than expected. The older picture of cosmic dawn begins with a universe that is almost smooth. After the first hot expansion, matter cools, light begins to travel freely, and the cosmos settles into a wide field of ordinary gas and invisible dark matter. The ordinary gas is mostly hydrogen with helium beside it, and almost nothing heavier. The dark matter does not shine, but its gravity matters from the beginning. It gathers first, forming the invisible framework into which ordinary gas can fall. This model is not a loose guess. It grows out of many lines of evidence, including the afterglow of the early universe, the distribution of galaxies across large distances, and the way gravity shapes matter on enormous scales. In that framework, the first galaxies are expected to appear through a gradual chain. Small differences in density become important because gravity strengthens them over time. A region with slightly more matter pulls in more material. As more matter gathers, the pull deepens. Gas falls inward, cools, and becomes dense enough to form stars. The first stars then light the first galaxies, but those galaxies are not expected to look mature at once. They are expected to be small systems, still assembling, still poor in heavy elements, and still limited by the short time available. This is the slow sunrise that Webb was expected to examine. The word slow does not mean inactive. It means limited by physical steps that cannot be skipped easily. Gas has to collapse before it can make stars. Gas also has to cool, because hot gas resists falling into compact knots. Once stars begin to form, the most massive stars produce strong radiation and powerful winds. Later, some of them explode, heating the surrounding gas and pushing it outward. This feedback can slow further star formation by disturbing or removing the raw material needed to build more stars. A young galaxy therefore grows through a balance between gravity pulling gas inward and stellar activity pushing gas back. The balance allows growth, but it does not usually allow unlimited growth. In nearby galaxies, star formation is inefficient. Much of the gas does not become stars quickly, and some of it is stirred, heated, or expelled. The old expectation carried that lesson backward into the early universe, while allowing for differences in density and composition. Early galaxies could form rapidly compared with many later systems, but not so rapidly that they would already resemble large developed galaxies when the universe was only a few 100 million years old. Another reason for the expected simplicity is chemistry. The first gas contains almost no carbon, oxygen, silicon, iron, or other heavier elements. Astronomers often call these heavier elements metals, even when the word differs from everyday usage. They are made mainly inside stars and spread into space when stars die. That means a chemically rich galaxy carries a history of previous stellar generations. It has already formed stars, allowed some to live out their lives, and mixed their products into later gas. In the earliest galaxies, there should not have been much time for that cycle. Massive stars can live briefly, but even a fast enrichment process still requires stars to form, burn, die, and distribute their material. The slow sunrise model therefore predicts that the first galaxies should be chemically plain compared with later galaxies. They may show the earliest signs of enrichment, but they should not look as though many generations of stellar processing have already occurred. Their light should come mostly from young, hot stars forming out of simple gas. Their dust content should be low, because dust also depends on heavier elements. Their structure should be rough and compact, but not necessarily massive or settled. This expectation fits the broader idea of hierarchical growth. In the standard account, large galaxies are built from smaller systems. The first objects form inside small dark matter halos, then merge with other small objects, draw in fresh gas, and grow over long spans of time, over billions of years. These repeated mergers and steady gas flows produce larger galaxies, more complex shapes, and richer chemical histories. The Milky Way is not treated as something that appears whole in the first age of the universe. It is the result of many earlier stages, including smaller building blocks that formed, merged, and changed. This hierarchy does not require every galaxy to grow at the same rate. Some regions are denser than others, and some halos form earlier, but the general trend remains clear. The earliest visible galaxies should be the starting pieces of the later population, not finished examples of it. Webb was expected to find more of those starting pieces than any previous telescope could see. The scientific hope was strong because this picture had worked well across many other observations. Models based on expanding space, dark matter, ordinary matter, and gravity could reproduce the large-scale structure of the universe with impressive success. Computer simulations, while never perfect, showed small early galaxies forming first and larger systems emerging later. Observations from Hubble and ground-based telescopes supported a general rise in galaxy growth over time. Later galaxies were more numerous, more massive, and more chemically developed than the earliest known samples. The unknown region was cosmic dawn, where direct evidence was sparse. Webb entered that region with a clear task: find the faint systems predicted by the model, measure their light, and fill in the missing early chapters. Many astronomers expected surprises in detail, because new instruments usually reveal complexity, but the broad picture seemed stable. The earliest galaxies might be slightly more common, slightly brighter, or slightly stranger than expected. They were not expected to form a large population of luminous systems that would press hard on the timeline itself. The expected observations had a recognizable shape. deep Webb images should contain many faint red sources. Most should be small. Their light should suggest strong star formation but limited mass. Their spectra should reveal low chemical enrichment, with only early traces of heavier elements in many cases. The brightest objects should be rare, and any apparently massive galaxy from the first few 100 million years should be treated with suspicion until spectroscopy confirmed its distance and nature. This expectation did not come from underestimating the early universe. It came from known constraints. The universe had a finite age. Matter needed time to gather. Stars needed time to form. Heavy elements needed time to accumulate. Black holes needed time to grow from their first seeds. The timing was tight, and the slow sunrise model was a way of keeping each stage within that timing. If a galaxy appeared too bright too early, astronomers would first ask whether the brightness was misleading. If it appeared too massive, they would ask whether a smaller amount of stars could explain the light. If it appeared chemically rich, they would ask whether the spectral features had been interpreted correctly. The model allowed caution because the data near the edge of visibility would always be difficult. What Webb changed was not the value of caution, but the amount of evidence pressing against the simplest expectation. This slow, sunrise model still provides the foundation for interpretation. It explains why early galaxies should exist at all, how gravity creates structure, why dark matter halos matter, and why gas can form the first stars. The problem is not that the model expected darkness and found light. The problem is that the light appears too organized in too many places. Galaxies that should have been faint beginnings often appear brighter than anticipated. Some look compact and intense. Some show signs that chemical enrichment had already begun earlier or faster than expected. The early universe still follows the basic rules of structure formation, but Webb suggests that those rules may have operated in more efficient conditions than the older picture assumed. Gas may have collapsed more densely. Star formation may have produced more light per amount of mass. The first stars may have enriched their surroundings quickly. Early black holes may have contributed to the glow. Any of these adjustments can preserve the larger framework while changing the detailed pace. This is why the old story matters so much before the surprises are examined. Without it, Webb's discoveries would be only a list of distant objects. With it, they become a test. The telescope is comparing the expected childhood of galaxies with actual evidence from that time. The slow sunrise was a reasonable prediction built from real science. But the new observations suggest that cosmic dawn may not have been as gradual as the phrase implies. The next step is to see how the first deep fields began to reveal that tension, not through one dramatic object alone, but through a growing population of early galaxies whose brightness made the young universe look unexpectedly busy. Webb's early deep fields did not announce their importance through a single clear object. They began as crowded images of small sources, each one needing careful measurement before it could be placed in the history of the universe. A deep field is made by pointing a telescope at a small region of sky and collecting light for a long time, allowing very faint galaxies to emerge from the background. In Webb's first deep observations, the visible result was a dense field of galaxies at many distances and many ages. Some were relatively nearby in cosmic terms, with shapes that could be recognized more easily. Others appeared as small red sources near the limit of detection. Those faint red sources drew attention because their colors suggested that their light had been strongly stretched by cosmic expansion. If the estimates were right, some belonged to the first few 100 million years after the Big Bang. That was already an important achievement. Webb was finding the kind of early galaxy population it had been designed to study. The troubling part came when astronomers began estimating how bright some of these galaxies were. They were not all the faint, modest beginnings that the slow sunrise model had led many researchers to expect. Several appeared unusually luminous for their age, and the pattern repeated across more than one observing field. Brightness is not a simple measurement in the early universe. A galaxy can look bright for several reasons, and each reason has a different meaning. It may contain many young stars. It may contain a smaller number of unusually hot, massive stars that produce more light than ordinary stars. Its gas may be glowing strongly around regions of star formation. A central black hole may be feeding and adding light of its own. The galaxy may even be magnified by gravity from a massive cluster lying between it and Earth. Because of these possibilities, astronomers do not treat brightness as a direct count of stars, but brightness still matters because it sets a demand. Something inside the galaxy must be producing the observed light, and if the galaxy is truly very early, then that light has to be explained within a short amount of cosmic time. Webb's early sources made that demand harder than expected. Many appeared too luminous to fit comfortably into the simplest models of small young galaxies forming slowly out of simple gas. The issue was not that bright galaxies should never exist at high redshift. Dense regions of the early universe could form stars early, and rare objects are always possible. The issue was abundance and timing. Webb seemed to be finding more bright early candidates than many predictions had allowed. A rare bright source can be treated as an exceptional case. A larger population suggests that the conditions of the early universe may have favoured more rapid star formation than expected. In simple terms, the telescope was not only finding the first sparks, it was finding evidence for vigorous activity. Some of these galaxies appeared to be forming stars at high rates. Some seemed compact, concentrating their light into small regions. Some had colours that suggested strong emission from gas heated by young stars. Each property could be understood individually. Together, they began to make cosmic dawn look less like a slow and thin beginning and more like a period of intense early growth. This does not mean the early universe broke its own rules. It means the rules may have operated in conditions that earlier models did not capture fully. Gas in the young universe was denser on average than it is today. Galaxies were smaller, and matter could gather into more compact regions. If gas collapsed efficiently into dark matter halos, star formation could proceed rapidly. If the first stars were more massive than stars forming today, they would produce more light per unit of stellar mass. If feedback from young stars did not expel gases effectively in the smallest early systems, those galaxies could continue making stars at a faster pace. Each of these ideas is physically reasonable, but the data must determine how much each one contributes. Webb's brightness problem is therefore not a single contradiction. It is a set of connected questions about efficiency. How efficiently did early galaxies turn gas into stars? How much light did those stars produce? How often did gas emission brighten the measurements? How often did black holes add hidden power at the centre? The answers affect how massive the galaxies really were and how difficult they are to explain. This is why many of the first dramatic claims were treated carefully. Some early sources were identified using photometric redshifts, which rely on brightness measured through filters rather than detailed spectra. That method is valuable for searching large areas, but it can confuse different kinds of red objects. A dusty galaxy at a later time can resemble a much earlier galaxy. A strong emission line can make a source look brighter in one filter, changing the inferred distance or mass. Gravitational lensing can magnify a background galaxy, making it appear more luminous than it would without the lens. Astronomers know these risks well, so the first step after discovery is not certainty. It is testing. The candidates are compared with models, observed again when possible, and selected for spectroscopy if they are important enough and bright enough for detailed follow-up. Some early claims became less extreme after this process. A few objects that first appeared very massive or very distant were revised. That revision is not a failure of Webb. It is part of turning early images into reliable science. What made the overall result remain important is that the whole pattern did not vanish, even after caution, corrections, and better measurements. Webb continued to show that luminous galaxies existed earlier than expected in significant numbers. The field moved from surprise toward a more precise problem. The question was no longer whether every early bright object was exactly what it first seemed. The question became why so many early objects were bright enough to be found at all. This shift is important because it protects the subject from exaggeration. Webb did not show mature modern galaxies lined up at the beginning of time in a simple or unquestionable way. It showed that the early galaxy population was brighter and more active than many models had predicted. That is a subtler result, but scientifically it is more durable. It leaves room for measurement errors in individual cases while still requiring a broader explanation. A calm interpretation begins with stars. Young massive stars are extremely luminous. If early galaxies formed many of them at once, their ultraviolet light would be strong. And after redshift, that light would arrive in Webb's infrared bands. These galaxies might not need to contain as much stellar mass as their brightness first suggests if their stars were unusually efficient light producers. This possibility connects to the composition of the early gas. With fewer heavy elements, gas cools and fragments differently. The earlier stellar populations may have been weighted toward more massive stars than the populations common today. Such stars live briefly, shine intensely, and affect their surroundings strongly. They can brighten a young galaxy while also beginning chemical enrichment. However, this explanation has limits. It has to match the measured colors, the shape of the spectra, and the number of galaxies observed. A population of massive stars can help, but it may not solve every case. Glowing gas adds another layer. Around young stars, hydrogen and other elements can emit strong light at specific wavelengths. When redshift moves these emission lines into Webb's observing bands, they can raise the apparent brightness of a galaxy. If this contribution is not properly separated from starlight, the galaxy's stellar mass may be overestimated. Spectroscopy is especially useful here because it can identify these lines and show how much of the light comes from gas rather than stars. In several early galaxies, strong emission lines appear to be an important part of the signal. This reduces some of the tension, but it also confirms that the galaxies are physically active. Strong gas emission means intense radiation from young stars or from an active central source. It does not restore a quiet cosmic dawn. It changes the explanation for the brightness while keeping the early activity in place. Feeding black holes complicate the interpretation further, but they belong more fully to a later part of the story. For the brightness question, their role is simple. A black hole pulling in gas can produce enormous light from a compact region. If some early galaxies contain active black holes, their total brightness may exaggerate the amount of stellar mass present. This would ease the problem of building too many stars too soon. At the same time, it would raise a different problem how those black holes formed and grew so early. The brightness may move from one engine to another, but it does not disappear. Webb's early fields therefore show a young universe with more engines of light than expected, and with those engines already operating when the timeline was still short. The most measured conclusion is that cosmic dawn was not merely the first appearance of small galaxies. It was a period in which some galaxies were already efficient, compact, and luminous. The early deep fields revealed this not as a completed answer, but as a population-level pressure on the old view. The young universe had found ways to shine strongly, and each explanation for that light points to faster growth, denser environments, more efficient star formation, or early black hole activity. This is where the first unease became a structured scientific problem. Brightness led to estimates of mass, and mass would soon make the tension sharper, because some of Webb's early candidates appeared not only bright, but heavy enough to challenge the available time even more directly. The mass estimates placed on Webb's earliest galaxy candidates turned the brightness problem into a sharper test of cosmic growth. Brightness can come from several engines, and a luminous source does not automatically mean a galaxy has already built an enormous population of stars. Mass is more demanding. If a galaxy truly contains many billions of stars only a few 100 million years after the Big Bang, then those stars must have formed, gathered, and settled within a short interval. The issue becomes how much ordinary matter had already been converted into stars, how quickly gas could fall into a dark matter halo, and how efficiently early star formation could proceed before feedback pushed gas away. This is the setting in which a small group of Webb sources became known as universe breakers. The nickname was stronger than the evidence deserved, but the scientific discomfort behind it was real. In the first estimates, these compact red sources appeared to contain far more stellar mass than standard models expected at such early times. Their colours suggested that their light came from roughly 500 to 700 million years after the Big Bang. At that age, very massive galaxies should have been rare, yet the first analysis suggested that some candidates might contain stellar masses approaching those of large modern galaxies. In the most extreme reading, a few seemed uncomfortably close to the mass scale of the Milky Way. That comparison mattered because the Milky Way is not an object that appeared whole near the beginning. It is a large galaxy shaped by long growth, mergers, gas flows, star formation, and chemical enrichment across most of cosmic history. Finding anything even remotely comparable in stellar mass near cosmic dawn would place severe pressure on the timeline. It would mean that a large fraction of available gas had already become stars where only a short period had passed since the first structures could form. The difficulty can be understood through the basic steps of galaxy growth. A young galaxy starts with gas, mostly hydrogen and helium, inside a dark matter halo that supplies most of the gravity. For the galaxy to become massive in stars, gas has to fall inward, cool, fragment, and collapse into star-forming clouds. Those clouds then have to produce stars at high rates. Massive young stars immediately affect the surrounding gas through radiation, winds, and later explosions. This activity can compress some gas, but it can also heat and expel gas, reducing the fuel available for the next generation. Growth, therefore, has built-in resistance. The fastest formation of stars is limited not only by how much gas exists, but by how quickly that gas can be gathered and retained. If the universe breaker candidates were truly as massive as first reported, they would require exceptionally efficient conversion of gas into stars. Early halos would need to collect ordinary matter quickly, hold onto it strongly, and form stars with much less delay or waste than expected. That would require a young universe in which the first galaxies were far better at building stellar mass than familiar galaxies are today. This is why the candidates caused debate. They challenged the expected relationship between time, gas supply, and stellar growth. A galaxy can shine brightly for a short time if it contains hot massive stars. It can appear bright if gas emission adds to the light, but a very high stellar mass is harder to explain because it represents accumulated formation. It is a record of previous star birth, not only a temporary bright phase. If large stellar masses were confirmed at very high redshift, the early universe would need unusually massive dark matter halos appearing sooner than expected, star formation efficiencies much higher than normally allowed, or a different balance between stars, gas, dust, and black holes than the first estimates assumed. Each possibility changes the picture in a different way. Higher efficiencies change galaxy formation physics. Early massive halos affect the growth of structure. Hidden black hole light changes the interpretation of the observations. All are possible areas of research, but none can be accepted without stronger evidence. The important caution is that the first universe breaker claims were based mostly on photometric data. Photometry measures brightness through filters. From those measurements, astronomers can estimate a source's redshift, age, stellar mass, and dust content by comparing the observed colours with model galaxies. This is a powerful method when spectroscopy is not yet available, but it has a known weakness. Different physical situations can produce similar colours. An old or dusty galaxy at a lower redshift can sometimes resemble a very distant young one. Strong emission from gas can increase the light in certain filters and make the galaxy seem more massive than it is. An active central black hole can add compact red light that does not come from ordinary stars. Dust can hide young blue light and make a source appear older. The models used to infer mass must choose among these possibilities, and the choice affects the result. Near the detection limit, even small uncertainties can produce large changes in the inferred mass. For this reason, many astronomers responded to the universe breaker candidates with interest, but not immediate acceptance. The proper question was not whether Webb had disproved cosmology. It was whether the sources had been placed at the correct redshifts, and whether their light had been correctly assigned to stars. Follow-up work began separating these issues. Some candidates received stronger observations, some were revised downward in mass. Some of the most extreme early interpretations became less severe. Once more, careful modelling accounted for emission lines, dust, or possible black hole contribution. In a few cases, objects that first looked extraordinary became more ordinary, or at least less damaging to the standard picture. This is a normal outcome in frontier astronomy. The fact that some candidates softened under scrutiny is not a reason to dismiss Webb's early results. It is the way the reliable result is created. The more durable finding is that the population still contains early galaxies that are brighter, more compact, and in some cases more massive than expected, even after the largest claims are reduced. The nickname may have overstated the case, but it pointed toward a real tension. The question shifted from whether a few objects had instantly broken the universe to whether early galaxy formation models had underestimated how efficiently the first systems could build stars and produce light. That narrower question is less sensational, but more scientifically serious. It allows room for individual corrections while preserving the broader pattern. There may not be a need to discard the standard cosmological framework, but there is a need to improve the treatment of early star formation, feedback, dust, black hole activity, and the first dark matter, halos. Webb's data are pressing on the details of how the framework becomes visible structure. The mass estimates also raise a statistical issue. If an early survey finds one very massive candidate in a small patch of sky, astronomers must ask how common such objects are. A rare object in a dense region may be possible within the standard model. A large number of similar objects across independent fields is harder to absorb. Wider surveys help show whether the first detections were exceptional or part of a larger population. This is why the universe breaker debate became part of a continuing effort to measure the abundance of bright, massive galaxies across more fields and with better spectra. The stakes are clear. The number of massive galaxies at early times is directly connected to the number of massive halos available to host them. If there are more massive galaxies than halos predicted by the model, then either the observations are being overestimated or the model is missing something about early structure. If the number of halos is sufficient but the galaxies inside them are brighter than expected, then star formation physics may be the main issue. If black holes are adding much of the light, then the early growth of black holes becomes central. These alternatives lead to different revisions and different future tests. The universe breaker candidates therefore serve as a diagnostic. They force astronomers to examine each link in the chain from dark matter concentration to gas collapse, from gas collapse to star formation, from star formation to emitted light, and from emitted light to the measured Webb signal. The lasting value comes from reducing apparent impossibility into specific questions. How early can a massive dark matter halo form? How much gas can it draw in? How efficiently can that gas become stars in a low metallicity environment? How strongly does feedback limit growth? How often do compact black holes contaminate the light? How many such systems exist per volume of space? Together, these questions define the pace of cosmic dawn. The universe breakers may not literally break the universe. They reveal where the previous picture was too simple. They show that mass in the early universe is not only a matter of counting stars, but of understanding every process that can imitate, accelerate, or limit stellar growth. The next stage is to remove the disguises more directly, because only detailed spectra can decide whether the light belongs to ancient stars, hot gas, dusty nearer systems, or feeding black holes. Until that separation is made, the mass problem remains partly open, but it is no longer vague. It has been narrowed into measurable causes, and the path forward runs through the fingerprints hidden inside the light itself. Spectroscopy gives Webb's early galaxy discoveries their strongest test because it changes the evidence from a broad colour estimate into a detailed measurement of light. A distant source in an image can be suggestive, but it remains ambiguous until its light is separated by wavelength and examined more carefully. This process matters especially near cosmic dawn, where the objects are faint, compact, and difficult to distinguish from several possible imposters. In a broad image, a small red source may look like a very early galaxy because its light appears only at longer infrared wavelengths. Yet the same appearance can be produced by a dusty galaxy at a later time, by unusually strong emission from gas, or by light from matter falling toward a central black hole. Spectroscopy reduces that ambiguity. It takes the combined light from the source and spreads it into a spectrum, showing how much light arrives at each wavelength. Within that spectrum are features produced by atoms, ionized gas, stars, dust, and sometimes an active black hole. These features do not give every answer at once, but they allow astronomers to ask more precise questions. The first and most important question is whether the object is truly distant. For a galaxy near cosmic dawn, one of the key signs is a sharp break where shorter wavelength light has been absorbed by hydrogen gas. The position of that break tells astronomers how much the light has been shifted by expansion. If the break appears at the right infrared wavelength, the galaxy may be very far away. Spectroscopy can locate this break more securely than filter colours alone. It can also identify emission lines, which are bright features produced when gas absorbs energy and then releases light at specific wavelengths. If several lines appear together in the pattern expected for known elements, and if the whole set is shifted by the same amount, the redshift becomes much harder to dispute. The object is then no longer only a candidate selected by colour, it becomes a confirmed early galaxy, placed on the cosmic timeline by its own measured light. This distinction is central to the debate around Webb's troubling results. Early photometric candidates can be exciting, but they are provisional. Spectroscopic confirmations carry more weight because they remove many of the easiest explanations for error. The first disguise is the dusty lower redshift galaxy. Dust absorbs and scatters shorter wavelength light, leaving a galaxy looking red even when it is not close to cosmic dawn. If only a few filters are available, such a galaxy can resemble an object whose light has been stretched by extreme expansion. Spectroscopy tests this by looking for the correct break and the correct pattern of lines. A dusty nearer galaxy will usually place its features at different wavelengths from a true high redshift galaxy. Its spectrum may show signs of older stars, heavier dust absorption. or emission lines that match a later cosmic time. Once those features are measured, the false distance can be corrected. The second disguise is the emission line problem. A young galaxy with intense star formation can produce very bright lines from glowing gas. If one of these lines falls inside a broad filter, it can make the source look brighter than it would from starlight alone. When models interpret that extra brightness as stars, they can overestimate the galaxy's stellar mass. This is one reason some early Webb candidates seemed unusually heavy. Spectroscopy can separate line emission from the smoother background of starlight. It shows whether the apparent brightness comes from a broad stellar population or from a few strong lines. In some cases, this reduces the inferred mass. The galaxy remains early and active, but it no longer requires as many stars as the first estimate suggested. This correction is important because it demonstrates both caution and progress. The evidence becomes less dramatic in some individual cases, yet more reliable overall. The third disguise is the active black hole. A black hole itself does not shine, but gas falling toward it can heat strongly and produce large amounts of radiation. In a small distant galaxy, that compact source of light can be difficult to separate from starlight. If the black hole is feeding rapidly, it can make a galaxy appear brighter, more massive, or more mature than it really is. Spectroscopy again provides clues. Gas moving near an active black hole can produce broad emission features because the material is travelling at high speed. The ionization state of the gas can also be unusual, showing that it has been exposed to intense radiation. The shape of the spectrum may reveal a strong central engine rather than a galaxy powered only by stars. This does not make the object unimportant. It changes the nature of the problem. If a black hole explains some of the brightness, then the stellar mass tension may soften. But the early black hole growth problem becomes stronger. The light has not stopped being surprising. It has been assigned to a different physical cause. Spectroscopy also helps measure chemical enrichment, although this becomes more difficult at the faintest limits. The first stars formed from nearly pure hydrogen and helium, while heavier elements were created later inside stars and spread by stellar deaths. When a spectrum shows features linked to oxygen, carbon, or other heavier elements in a very early galaxy, it suggests that some enrichment had already occurred. That conclusion depends on careful interpretation, because spectral lines can be faint and blended with noise. Still, when the evidence is strong, it gives astronomers a way to test the pace of early stellar evolution. A chemically enriched galaxy at high redshift implies that earlier stars had already formed and returned processed material to the surrounding gas. Spectroscopy does not merely say that the galaxy is far away. It begins to describe what kind of environment existed there. The same method can reveal whether a galaxy is forming stars intensely by measuring lines associated with hot young stars and ionized gas. It can show whether the source is compact and energetic rather than extended and calm. It can also help estimate how much dust is present, which affects how the light should be interpreted. Each piece of the spectrum narrows the range of possible explanations. This is why follow-up work after Webb's first images has been so important. Some early claims have become less extreme, and that is expected. Spectroscopy has shown that certain objects are not as massive as photometry first suggested, or that their light includes strong gas emission, or that a black hole may contribute. But the larger pattern has not been erased. A growing set of spectroscopically confirmed galaxies still lies in the first several 100 million years of cosmic time, and many of them are brighter or more active than older models predicted. The strongest scientific result is therefore balanced. Webb did not turn every surprising candidate into an impossible galaxy. It turned enough of them into real early objects to keep the pressure on theory. The disguises matter because they prevent overstatement. The surviving conformations matter because they prevent dismissal. This is the position the field now occupies. The early universe is not being judged from a single dramatic image. It is being reconstructed from repeated measurements, each one asking whether the light has been stretched by expansion, whether gas has added brightness, whether dust has changed the colour, whether a black hole is present, and how much stellar mass remains after these effects are accounted for. That reconstruction is still incomplete, but it is already more detailed than anything available before Webb. It shows a cosmic dawn that contains real galaxies earlier than expected, with strong star formation and in some cases signs of rapid development. The conclusion is not simple failure of the old model. It is a tightening of the evidence around the parts of the model that need refinement. Spectroscopy has changed the question from whether Webb was seeing tricks of colour into how the confirmed objects formed so efficiently. It has removed the easiest disguises from many sources, and where it finds a disguise, the disguise often introduces a new problem of its own. Dust requires earlier enrichment. Strong gas emission requires intense radiation. Active black holes require early black hole seeds and rapid growth. Each correction reshapes the tension rather than making it vanish. The next step is to examine the farthest confirmed examples, where spectroscopy has placed galaxies at the edge of current measurement, and where the same issues of brightness, compactness, and enrichment appear under the most demanding time limit. At that distance, the evidence has very little room to hide inside a comfortable timeline. The farthest confirmed galaxies matter because they compress the entire problem into the least forgiving part of the timeline. When a source is placed very close to cosmic dawn by spectroscopy, there is little room left for slow development. Every feature in the light has to be explained inside a young universe where only a limited interval has passed since the first matter began gathering into luminous structures. This is why record-holding galaxies attract so much attention. A new distance record is not only a point of pride for an observatory, it is a test of how early a real galaxy can be seen doing recognizable galactic work. Webb has pushed this test farther than previous telescopes by detecting sources whose light has been stretched into deep infrared wavelengths, and then confirming some of them through detailed spectra. In these cases, the redshift is no longer only an estimate from colour, it is measured from features in the light itself. That makes the object harder to dismiss as a lower redshift imposter, and it places its brightness, compactness, and chemical signs into a strict age. The farther the confirmed source, the stronger the demand placed on any explanation. A galaxy seen only a few 100 million years after the Big Bang is not allowed to borrow time from later cosmic history. Its stars, gas, and possible central engine all have to be present already. This is the quiet force behind Webb's most distant confirmed detections. They do not need to be large in a modern sense to be important. A small galaxy at an extremely early time can be more revealing than a massive galaxy seen much later, because it shows what structure formation had already achieved near the beginning. In some of these sources, Webb sees more light than expected for such an early stage. The light may not all come from stars, and that distinction remains essential, but the source is still real and early. Even if gas emission or a black hole contributes to the brightness, the physical environment must already be energetic enough to produce that signal. This means the young universe had already assembled dense regions where matter could collapse, heat, radiate, and organize into systems that Webb can identify across enormous distance and time. A farthest confirmed galaxy is therefore not just a distant object, it is a constraint. It sets a minimum level for what the universe had already accomplished by that moment. The features that make such a galaxy troubling usually appear together. It may be bright for its age, it may be compact, placing much of its light into a small region. Its spectrum may suggest strong ionized gas around young stars. In some cases, there may be signs that heavier elements were already present. None of these features is automatically impossible. Young stars can be bright, small galaxies can be dense, massive stars can enrich gas quickly. But the combination is what gives the evidence weight. A bright source could be explained by a short burst of star formation. A compact source could reflect a small dark matter halo concentrating gas. Chemical enrichment could come from earlier massive stars that lived briefly and died. Taken together at very high redshift, these features suggest that the earliest galaxies may have formed through more intense and efficient processes than the older slow picture assumed. The universe was not simply beginning to organize matter in a hesitant way. In some places, it had already produced focused engines of star formation and radiation. This changes how astronomers think about the first environments. A very early compact galaxy is not a large settled disk like the Milky Way. It is more likely a dense, irregular system, rich in gas and dominated by young stellar activity. Its small size does not make it weak. In a dense early halo, gas could flow inward rapidly and reach high pressures. Star formation could become concentrated, and the light from young massive stars could dominate the whole object. Because Webb sees the galaxy across such a long distance, many internal details remain unresolved. The telescope may not separate individual clumps or star-forming regions. What reaches the detector is a combined signal from stars, gas, dust if any is present, and perhaps a central accreting black hole. This is why a compact appearance must be interpreted carefully. Compact light does not necessarily mean a simple structure. It may be a cluster of bright regions blurred together by distance. Still, the compactness matters because it shows that strong radiation is emerging from a small early system, and this has consequences for growth, chemistry, and the clearing of surrounding gas. The record edge also sharpens the issue of ancestry. If a galaxy is visible at such an early time, it must have begun forming before the moment being observed. The stars producing the light were not born at the instant their photons left for Earth. Gas had already gathered, star formation had already begun, if heavy elements appear, an even earlier generation of stars had already completed its life cycle. If a black hole contributes, some seed had already formed and started growing. Each observed property points backward to an earlier stage that Webb may not yet see directly. The confirmed galaxy becomes a marker placed after hidden preparation. This is one of the deepest tensions in the subject. The visible object is already early, but its causes must be earlier still. Cosmic dawn, as Webb sees it, may already be the result of activity that began in the darker interval before the first confirmed galaxies. The farthest light is therefore not the beginning of the process. It is the first part of the process that current instruments can reliably measure. This helps explain why the record detections feel both successful and incomplete. They prove that Webb can reach extraordinary distances, but they also reveal how much remains just beyond reach. A spectrum can confirm a galaxy and show key features, yet the faintness of the source limits how much detail can be extracted. The lines may be weak. The continuum, the smoother background light from stars and other sources, may be difficult to measure. Estimates of stellar mass and age may depend on models that are uncertain for such unusual environments. The first stars may not have followed the same distribution of masses as stars today. Gas with very few heavy elements may cool and fragment differently. Dust may be scarce, but even small amounts can alter the observed light. A black hole, if present, can distort the apparent properties. These uncertainties do not remove the discovery. They define the work required to understand it. The farthest confirmed galaxies are secure enough to challenge expectations, but still difficult enough to resist simple description. The clearest conclusion is that the early universe became observable quickly. Within a short cosmic interval, some regions had gathered enough matter and produced enough radiation for their light to survive the long journey to Webb. That fact alone places pressure on models of early growth. It asks how dark matter halos formed, how ordinary gas entered them, how efficiently the gas became stars, and how the first radiation shaped the surrounding medium. A very early galaxy does not have to resemble a modern galaxy to be mature in certain specific ways. It may be young in age but already active in star formation. It may be chemically primitive but not chemically untouched. It may be small in size but powerful in radiation. This distinction prevents exaggeration while preserving the scientific surprise. Webb is not showing fully modern galaxies at the beginning of time. It is showing that some early galaxies reached levels of activity, brightness, and internal processing sooner than expected. That is enough to make the timeline more demanding. In this sense, the farthest confirmed light becomes a fixed point around which the larger story has to adjust. The models must allow the object to exist, but they must also account for the population around it. One record holder can be rare. Several confirmed high redshift galaxies across different fields begin to map a broader reality. Each new detection tests whether the first record was an exception or part of a pattern. So far, Webb has made the early universe look less empty and less gradual than the simplest prediction suggested. The record edge is not troubling because it ends the search. It is troubling because it opens an earlier layer of questions. If galaxies are already bright and compact there, then star formation began sooner. If chemical signs are present, enrichment began sooner. If black holes contribute, their seeds formed sooner. The farther Webb confirms a galaxy, the more tightly all these beginnings are compressed. The edge of current measurement has become a place where the universe appears young in age but not passive in behavior, and the next clue lies in the chemistry carried by that ancient light. Chemistry gives the early galaxies a second kind of clock, separate from distance. Redshift tells astronomers when the light left a galaxy, but the elements inside that light describe what had already happened before the light began its journey. This is why chemical enrichment matters so deeply in Webb's view of cosmic dawn. The first ordinary matter in the universe was simple. After the earliest hot phase, the cosmos contained mostly hydrogen and helium, with only tiny traces of a few light elements. It did not begin with carbon, oxygen, silicon, iron, or the other heavier elements that later became common inside planets, dust, and living chemistry. Those heavier elements had to be manufactured. The main factories were stars. In stellar cores, pressure and heat-forced light atomic nuclei to join into heavier ones. The process releases energy and allows a star to shine, but it also slowly changes the chemical contents of the universe. When massive stars die, they return newly made material to space through winds and explosions. Later generations of stars form from gas that has been partly enriched by earlier generations. A galaxy's chemistry therefore carries memory. It records not only the gas from which the galaxy formed, but also the stars that have already lived inside it or near it. In the early universe, that memory was expected to be short. A galaxy seen only a few 100 million years after the Big Bang should not have had many opportunities to build and recycle heavy elements. Some enrichment could happen quickly if massive stars formed early, because massive stars live short lives. But the more chemically developed a galaxy appears, the more previous stellar activity it requires. This is where Webb's early spectra become important. In some high redshift galaxies, astronomers find signs of oxygen, carbon, and other heavier elements and gas that belongs to a very young cosmic time. The exact abundance is difficult to measure, especially in faint galaxies near the limit of detection, but the presence of these features already has meaning. It says that the gas was not untouched. Stars had formed before the moment being observed, and some had already processed the original hydrogen and helium into heavier material. For a galaxy at cosmic dawn, This pushes the required beginning farther back. The visible galaxy is early, but its chemical history began earlier still. A simple way to understand the problem is to follow the necessary sequence. First, gas has to gather into a dense region. Then the first stars have to form. Some of those stars have to be massive enough to evolve quickly. They must burn their fuel, die, and release heavy elements. That enriched gas then has to mix with surrounding material and appear in the light that Webb observes. None of these steps is optional. If a spectrum shows enrichment, the sequence must have happened before the light left the galaxy. The more enriched the galaxy is, the more efficient or rapid the sequence must have been. This is not a contradiction of stellar physics. It is a pressure on timing. The calendar supplied by redshift is short, while the chemistry suggests that the early galaxy had already passed through several developmental stages. The first stars are central to this question. Astronomers often describe them as population 3 stars, meaning stars formed from almost pristine hydrogen and helium. No such star has yet been directly identified with certainty. They are predicted because the early universe needed a first generation before any enriched stars could exist. Their properties are still uncertain, but theory suggests they may have been more massive on average than stars forming today. The reason lies in cooling. Heavy elements help gas clouds lose heat and fragment into smaller pieces. Without those elements, early gas may have remained warmer and collapsed into larger masses before forming stars. If many first stars were very massive, they would have been extremely bright and short-lived. They could have produced strong ultraviolet radiation, influenced nearby gas, and ended their lives quickly enough to enrich young galaxies within a brief time. This possibility helps explain why Webb may be seeing heavy elements earlier than older expectations suggested. Massive stars can move the chemical clock forward rapidly, yet this explanation has limits. It must account not only for the existence of heavy elements, but for the amount of enrichment, the number of enriched galaxies, and the way those elements were mixed into the gas. A single generation of massive stars can produce material quickly, but whether it can enrich an entire galaxy to the observed level depends on how many such stars formed, how they exploded, how their material spread, and how much pristine gas continued to fall in afterward. Early galaxies were not closed containers. Gas could enter from the surrounding cosmic web. Explosions could push material outward. Radiation could heat nearby gas and slow collapse. Mixing may have been uneven. Some regions could become enriched while others remained almost pristine. Webb often sees these galaxies as unresolved or barely resolved sources, so a measured spectrum can blend many internal environments together. This makes interpretation difficult. A chemical line may represent a compact star-forming region rather than the whole galaxy. Even so, the detection still shows that enrichment had begun, and that beginning was earlier than the simplest models expected. Dust adds another related clue. Dust grains form from heavier elements, especially carbon, silicon, oxygen, and metals produced by stars. In the nearby universe, dust shapes how galaxies appear by absorbing ultraviolet light and re-emitting energy at longer wavelengths. In the earliest galaxies, dust was expected to be scarce because the necessary elements had not had much time to accumulate. When Webb and other observations suggest dust in very early systems, the same timing issue appears again. Dust requires previous stars. It may form in the cooling ejecta of supernovae or in the winds of evolved stars, though the earliest contribution likely comes from massive stars that die quickly. If dust appears at high redshift, then the young galaxy is not chemically untouched. It has already experienced enough stellar processing to make solid particles, or at least enough heavy material to affect its light. Dust can also complicate mass estimates by reddening the galaxy and hiding younger stars, so it is both a clue and a source of uncertainty. chemistry also connects to the brightness problem. Heavy elements help gas cool. When gas cools more efficiently, it can collapse into denser clouds and form stars more readily. Once the first stars enrich their surroundings, later star formation can change character. The galaxy may become better at producing many stars, including lower mass stars that live longer. This creates a feedback loop in the early history of a galaxy. The first massive stars enrich the gas. The enriched gas cools differently. New stars form from a changed chemical environment. More stars then add more radiation and more enrichment. In a compact early galaxy, this cycle could proceed quickly, especially if fresh gas continued to flow inward. Such a process would help explain how some early galaxies became bright and chemically developed in a short time. It does not remove the difficulty, but it gives the difficulty a physical path. The young universe may have contained small regions where star formation and enrichment were concentrated, rapid and self-reinforcing. The remaining question is how common those regions were. If only a few galaxies show early enrichment, they may represent rare dense peaks where structure formed ahead of the average. If enrichment appears widely among confirmed early galaxies, then the first generations of stars may have transformed the young universe more rapidly than expected. This is why astronomers need larger samples and better spectra. Individual detections are valuable, but the population determines the scale of the revision. Webb has begun to show that heavy element production was already underway during cosmic dawn. Future observations must measure how much enrichment existed, how it varied from galaxy to galaxy, and whether the earliest visible systems were chemically unusual or part of a broader pattern. That distinction will shape the next version of the cosmic timeline. The troubling implication is therefore precise. The early galaxies are not merely bright points placed far away by redshift. Some carry evidence that stellar life cycles had already begun changing the raw material of the universe. The first stars did not only light their galaxies, they altered them. They supplied heavier elements, changed how gas cooled, and prepared the conditions for later generations of stars. Webb is seeing that transformation closer to the beginning than expected, and every chemical feature in an early spectrum pushes attention back toward an even earlier, dimmer phase where the first stars formed and died before direct evidence becomes easy to find. The next stage of the story is not only about what those stars made, but how their radiation changed the space around them, because the young universe was still filled with hydrogen gas that could block light until the first galaxies began clearing a path through it. Before the first galaxies could make the universe transparent, they formed inside a medium that was still difficult for light to cross. The early cosmos was filled with hydrogen gas spread through space, and much of that gas was neutral, meaning its electrons remained attached to its protons. Neutral hydrogen has a strong effect on certain forms of ultraviolet light. It can absorb that light efficiently, preventing it from travelling freely across large distances. This condition created what astronomers call the cosmic dark ages. The phrase does not mean that nothing existed. Matter existed. Gravity was working. Dark matter halos were growing. Gas was falling into the earliest dense regions, but there were not yet many luminous objects, and the hydrogen between those objects could block much of the light they produced. The universe was not fully transparent in the way it later became. For Webb's story, this matters because the first galaxies were not only building stars, they were also changing the state of the space around them. Their radiation began to alter the hydrogen gas that filled the young universe, and that alteration became one of the great transitions in cosmic history. The process is called reionization. It begins when energetic light from young stars, and possibly from feeding black holes, strikes neutral hydrogen and removes electrons from the atoms. Once hydrogen is ionized in this way, it no longer absorbs the same ultraviolet light as effectively. Regions around young galaxies can become clearer, allowing more radiation to escape. Ionization did not happen everywhere at once. It was uneven. The earliest galaxies likely created ionized regions around themselves, and those regions grew as more light was produced. Over time, separate ionized regions expanded and joined, until most of the hydrogen between galaxies had been transformed. The universe gradually became transparent to the kinds of light that had previously been blocked. This transition marks the end of the Dark Ages and the beginning of a cosmos in which galaxy light could travel over large distances with less interference. The timing of this transition is one of the key questions Webb was built to help investigate. Before Webb, observations suggested that ionization was mostly complete by roughly the first billion years of cosmic history, but the exact pace and early stages remained uncertain. The older expectation was that the process would build gradually. The first galaxies were thought to be small and faint, so their combined radiation would take time to clear the hydrogen around them. If they formed stars slowly, they would produce ionizing light slowly. If much of that light was trapped inside the galaxies by gas and dust, then the surrounding universe would clear even more slowly. In this view, the earliest galaxies should often be hidden behind the effects of neutral hydrogen, and certain spectral signals should be difficult to detect from the deepest part of cosmic dawn. Webb's observations have made this picture more complicated. Some very early galaxies appear bright enough, active enough, or clear enough in their surroundings to let light escape sooner than expected. In a few cases, astronomers have reported signals associated with hydrogen emission at extremely high redshift, where the surrounding intergalactic gas should still have absorbed much of that light. The most important of these signals is often described as Lyman alpha emission, a specific form of light released by hydrogen. It is valuable because it can help confirm distance and reveal active star formation, but it is also fragile in the early universe. Neutral hydrogen between the galaxy and the telescope can scatter or absorb it. If this signal is detected from a very early galaxy, it suggests that the light has found a path through a region that is already at least partly ionized. That does not mean the entire universe was transparent at that time. It means the galaxy may have cleared a local region around itself, or may sit inside a larger ionized area created by several nearby galaxies. Either explanation points to early activity. A young galaxy capable of producing such a clear path must be emitting strong radiation, and it must be doing so in an environment where ionized regions can grow sooner than simple models predicted. This connects directly with the other Webb surprises. A galaxy that forms stars rapidly will produce many hot, massive stars. Those stars emit intense ultraviolet radiation. The same stars can enrich the galaxy when they die, and their radiation can ionize nearby gas while they live. A compact galaxy with concentrated star formation may be especially effective because much of its light is produced in a small region. If that light escapes through channels in the gas, it can ionize the surrounding medium and make the galaxy visible in ways that were expected to be rare at such early times. Feeding black holes, if present, could also contribute energetic radiation. They may help ionize gas beyond the reach of stars alone, although their frequency and importance at cosmic dawn remain uncertain. Reionization therefore becomes a meeting point for several problems. The brightness problem asks why early galaxies shine so strongly. The chemistry problem asks how stars had already processed simple gas into heavier elements. The transparency problem asks how radiation from these galaxies escaped into a universe that should still have been partly opaque. These are not separate mysteries. They are different consequences of early energy production. If the first galaxies were more efficient at forming massive stars, then they would be brighter, chemically influential, and better able to ionize their surroundings. If early black holes were common, they could add light and ionizing radiation while creating a new growth problem of their own. If dark matter halos assembled dense gas quickly, they could help build the compact systems that produce this radiation. Webb's evidence does not yet identify one final cause, but it shows that any successful explanation must account for several linked effects at once. The early universe was not only making galaxies, it was changing the conditions that determined which galaxies could be seen. This creates a difficult observational loop. Astronomers study ionization by observing early galaxies, but whether those galaxies are visible can depend on how far ionization had already progressed near them. The brightest and clearest objects may not represent the average young galaxy. They may be the ones living in the first ionized regions, where light had a better chance of escaping. Fainter galaxies may have been more numerous but harder to detect. Some may have contributed strongly to ionization even if they remain below Webb's current limits. This means the visible early galaxy population is shaped by both formation and transmission. Webb sees what formed, but it also sees what the surrounding hydrogen allowed to pass through. To reconstruct cosmic dawn, astronomers have to model both the sources of light and the medium between those sources and the telescope. A galaxy is not measured in isolation. Its light carries the history of the space it crossed. The most careful conclusion is that ionization may have been more uneven and locally advanced than the simplest gradual picture suggested. Some regions may have cleared early around unusually active galaxies, while other regions remained more neutral for longer. This unevenness is expected in broad terms, but Webb is beginning to place direct pressure on the timing. When strong early signals appear, they imply that ionized regions existed sooner or grew faster than many models anticipated. The young universe may have contained pockets of transparency around compact, star-forming systems, with these pockets expanding and merging over time. Such a picture does not require the entire cosmos to become clear all at once. It requires early galaxies to be capable of strong local influence. That is consistent with Webb's broader view of cosmic dawn as active, dense, and efficient in certain regions. It also explains why ionization is not only a background event, it is part of galaxy evolution itself. The first galaxies shaped their surroundings, and those surroundings then affected what later galaxies could form and how their light could travel. By clearing hydrogen, early radiation changed the universe from a place where many signals were trapped into one where starlight and galaxy light could move more freely. Webb is catching evidence from near the beginning of that transformation. The troubling part is not that ionization happened. It had to happen, because the later universe is transparent. The troubling part is how early some signs of clearing appear, and how naturally they align with the other signs of rapid development. Bright galaxies, early chemical enrichment, compact structure, possible active black holes, and unexpected hydrogen signals all point toward a cosmic dawn that was doing more work in less time than expected. The fog before transparency was not a passive background waiting to fade. It was altered by the first luminous systems, and Webb is showing that some of those systems may have been powerful enough to open paths through it sooner than the older timeline allowed. That realization leads naturally to the next problem. If the first galaxies produced more light than expected, then the source of that light has to be identified carefully, because not all early brightness belongs to stars. Some of it may come from compact engines hidden at the centers of young galaxies, where black holes were already feeding in the dark. The little red dots entered Webb's early universe studies as small, compact sources, but their importance comes from the kind of light they produce. They are faint in ordinary visual terms, yet many are strong in the infrared bands where Webb is most sensitive, and their appearance is unusually concentrated. In deep observations, they often look like tiny red points rather than broad young galaxies with visible structure. That compactness immediately raises a question about the engine inside them. A normal galaxy can be red because its light has been stretched by expansion, because dust changes its color, or because older stars contribute more of the glow. A very distant galaxy can also look red for all of those reasons at once. The little red dots are difficult because their spectra often seem to combine features that do not fit one simple category. Some parts of the light suggest stars, other parts suggest gas moving under much more extreme conditions in several cases. The evidence points toward a compact central source, possibly a feeding black hole embedded inside a young galaxy. That possibility matters because it changes the interpretation of Webb's brightest early objects. If a small galaxy contains a black hole pulling in gas, then a large fraction of its light may come from the heated material falling inward rather than from stars spread throughout the galaxy. This can make the galaxy appear more massive or more mature than it really is. In that sense, black holes may soften part of the galaxy mass problem. Some early systems that first looked packed with stars may instead be smaller galaxies whose brightness is being amplified by a central accreting engine. But the solution immediately creates another problem. A black hole bright enough to matter at cosmic dawn must already have grown substantially. It must have formed early, found gas quickly, and fed efficiently while the universe was still young. A correction to the stellar mass problem becomes a new challenge for black hole formation. This is why the little red dots have become more than a technical detail. They may be evidence that black holes were common and active much earlier than expected. A black hole does not emit light from within its event horizon, the region from which nothing can escape. The light comes from outside, where gas loses energy as it spirals inward. The gas heats, compresses, and radiates before crossing the final boundary. In a large nearby galaxy, this process can produce an active galactic center bright enough to outshine the stars. In the early universe, the same process would be harder to identify, because the whole source may be only a small unresolved point to Webb. Spectroscopy becomes essential. Broad emission lines can reveal gas moving at high speeds near a compact massive object. Certain ionization patterns can show that the gas is being exposed to radiation harder than ordinary young stars usually produce. Variability, when detectable, can also suggest a compact engine. None of these signs is perfect alone, but together they can distinguish a feeding black hole from a galaxy powered only by star formation. The difficulty is that early galaxies themselves were extreme. Hot, massive stars, dense gas, low chemical enrichment, and strong radiation fields can produce unusual spectra even without a black hole. This makes the little red dots a careful classification problem rather than a simple discovery label. They may not all be the same kind of object. Some may contain active black holes. Some may be compact dusty star-forming galaxies. Some may be dense stellar systems whose early stars produce unexpected colours. A mixed population is likely, and sorting it will take deeper spectra, longer monitoring, and comparison across many fields. The black hole interpretation becomes especially interesting because of growth limits. In the standard picture, the first black holes may form from the deaths of massive stars or through the collapse of dense gas under special conditions. If a black hole begins as the remnant of a first star, it may have only tens or hundreds of solar masses. To become millions of solar masses by cosmic dawn, it must grow quickly. But growth by feeding is not unlimited. As gas falls inward and shines, the radiation pushes outward on surrounding material. At a certain rate, this outward pressure can balance the inward pull, making it difficult for the black hole to keep eating faster. This balance is often called the Eddington limit. It is not an absolute wall in every situation, but it describes a natural restraint. If many little red dots host massive black holes only a few 100 million years after the Big Bang, then either some black holes were born from larger seeds, or they fed above the usual limit for periods of time, or dense early environments supplied gas in ways that models have not fully captured. Each option is scientifically plausible enough to investigate, but each requires conditions that were more favourable to rapid growth than the older picture assumed. Large seed black holes could form if enormous gas clouds collapsed directly rather than first making ordinary stars. This direct collapse idea has been explored for years because it can give the early universe a head start. Instead of beginning with a small stellar remnant, the black hole begins already much heavier. It then needs less time to reach the masses implied by some early observations. The challenge is that direct collapse requires particular conditions. Gas must avoid fragmenting into many stars, lose angular momentum, and fall inward efficiently. Radiation from nearby stars may help by preventing certain cooling pathways, but the environment has to be unusual. If little red dots are common black hole systems, then such favourable conditions may have occurred more often than expected, or another formation route may be needed. Faster feeding is another possibility. In dense young galaxies, gas may flow inward in bursts, allowing a black hole to grow rapidly for short intervals. The average growth over time might still respect broad physical limits, while brief episodes exceed the simple, steady picture. This would fit a young universe where gas fractions were high and galaxy centres were unsettled. Yet it also requires that enough gas reach the central region without being blown away by radiation, star formation, or explosions. The early galaxy has to feed its black hole while also forming stars and enriching its gas. These processes compete and interact. A feeding black hole can heat or expel gas, limiting star formation. It can also stir the surrounding medium and perhaps help clear paths for radiation to escape. In a compact early galaxy, the boundary between black hole growth and galaxy growth may be especially close. The little red dots may therefore represent a stage where both are happening together, before the system becomes large enough to separate its components clearly. Their redness remains one of the open clues. Red light can indicate dust, and dust itself implies earlier chemical enrichment. It can also reflect the shape of radiation from an accreting black hole, or a combination of stars and hot gas. If dust is present in many of these objects, then the chemistry problem returns. Dust requires heavy elements, which require earlier stars. If the redness comes mainly from black hole activity, then the growth problem becomes central. If it comes from dense stellar populations, then the star formation problem remains. The same small red appearance can therefore lead to several different histories, and Webb's task is to separate them without forcing one answer across the whole class. This is one reason the little red dots are valuable. They do not merely add another mystery to the list. They help identify which engine is responsible for part of the early light. Once astronomers know how much brightness comes from stars and how much comes from black holes, they can revise estimates of galaxy mass, star formation rate, and black hole abundance. The result may reduce some tensions while sharpening others. A universe with fewer massive early galaxies but more active early black holes is still a fast-developing universe. It has moved the pressure from stellar assembly into black hole seeding and accretion. A universe with many compact dusty starbursts is also demanding, because it requires rapid star formation and early enrichment. A universe with both is more complex than the slow sunrise model, but not beyond scientific description. It points to dense early environments where gas, stars, dust, radiation, and black holes evolve together at a pace that earlier observations could not reveal. The little red dots show why Webb's troubling discoveries cannot be reduced to one claim about galaxies being too big. The early universe may have looked bright because several engines were operating at once. Stars were forming intensely. Gas was glowing under strong radiation. Heavy elements and dust were beginning to appear. Black holes may have been feeding inside small systems. Each engine changes the others, and each leaves a partial imprint in the light. Webb has made those imprints visible, but the interpretation is still being refined. The next section gathers these threads into the broader revision now taking shape. cosmic dawn may not have been a gentle sequence of separate steps. It may have been a compact, efficient phase in which structure, chemistry, radiation, and black hole growth advanced together much faster than the older picture expected. A faster cosmic dawn is now the most careful way to describe what Webb has placed before astronomy. The phrase does not mean that the universe ignored known physics, and it does not mean that the standard cosmological framework has failed in a simple way. It means that the first visible stages of galaxy formation appear more efficient, more concentrated, and more rapidly connected than many older models expected. The evidence has arrived from several directions, and that is why it has become difficult to treat the result as a single measurement problem. Webb has found early galaxies that are brighter than anticipated. It has confirmed some sources at very high redshift, where the available time for growth is short. It has revealed spectra that suggest intense star formation, strong gas emission, and in some cases chemical enrichment earlier than expected. It has raised the possibility that compact active black holes were present inside small young galaxies. It has also shown that some early systems may have influenced the hydrogen around them strongly enough to help clear local paths through the cosmic fog. None of these clues alone would require a major change in thinking. Together, they suggest that cosmic dawn was not a slow, evenly paced transition from darkness into structure. It was more likely a patchy and vigorous period, with some regions advancing far ahead of the average. The key word is efficiency. In the older picture, the first galaxies grew through known steps that took time. Dark matter halos gathered first. Ordinary gas fell into those halos. The gas cooled, collapsed, and formed stars. Massive stars returned energy and newly made elements to their surroundings. Radiation ionized nearby hydrogen. Black holes, if present, grew by feeding on gas. These steps remain part of the story. But Webb suggests that in some early environments they may have happened with less delay and more overlap than expected. Dense halos may have collected gas quickly. Low metallicity gas, meaning gas with few heavy elements, may have formed stars with a different balance of masses. If more massive stars formed in the first generations, they would have produced more light, stronger radiation, and faster chemical enrichment. Compact galaxies may have concentrated this activity into small regions, making their light easier to detect across cosmic distance. Under those conditions, a young galaxy could look surprisingly bright without being a mature galaxy in the modern sense. It could be young, small, and unsettled, yet still powerful. That distinction is important because it prevents the interpretation from becoming exaggerated. Webb is not showing fully developed spiral galaxies identical to the Milky Way sitting at the start of time. It is showing early systems whose measured properties are stronger than expected for their age. Some may have less stellar mass than first estimated once gas emission, dust. Lensing and black hole light are accounted for. Some may be special objects found because they are unusually bright. Some may sit in rare, dense regions where structure began early. The careful revision is not that galaxies appeared finished immediately. It is that the first galaxies capable of being seen by Webb often seem unusually effective at turning available matter into light. That light can come from stars, ionized gas, and accreting black holes. And separating these sources is now one of the central tasks. The more carefully astronomers separate them, the more detailed the new picture becomes. A source that first seemed too massive may become less massive, but may reveal extreme gas emission. A galaxy whose stars seem too old may instead contain dust, which still requires earlier enrichment. A compact red object may reduce the stellar mass problem, but create a black hole growth problem. The tension moves, narrows, and changes shape, rather than simply disappearing. This is why Webb has not broken cosmology, but it has made cosmology more demanding. The standard model gives the broad setting and expanding universe, small early density variations, dark matter structure, ordinary gas, and gravitational growth. Webb is testing the astrophysics inside that setting. It is asking how gas behaves when the universe is younger, denser, and less chemically evolved. It is asking how the first stars differ from later stars. It is asking whether black hole seeds formed small and fed rapidly, or whether some were born large through direct collapse. It is asking how radiation escaped from young galaxies into a surrounding medium that was still partly neutral. These questions are not decorative details. They determine how quickly the universe changed from a smooth early state into a structured one. The early universe may have been governed by the same overall framework. While operating under local conditions that made growth faster in the places Webb is most likely to detect, selection effects also matter. Webb sees the objects bright enough to be found. The earlier surveys naturally favour the most luminous, compact, or strongly magnified systems. Many ordinary early galaxies may remain below current limits. This means the first Webb population is not necessarily a complete census of cosmic dawn. It may be a view of the most active peaks, but those peaks are still physically real, and their existence must be explained. A model cannot dismiss an object simply because it is rare if the surveys find too many examples of that rarity. Wider fields, deeper spectra, and better measurements will decide how representative these early bright systems are. If they remain uncommon, they will teach astronomers about the fastest routes to early structure. If they are widespread, the whole average history of early galaxy formation will need stronger revision. In either case, Webb has already shown that the first visible galaxies cannot be treated as a uniform population of faint beginnings. The dawn was uneven. Some regions lagged, some advanced quickly. The telescope is now mapping that unevenness with enough detail for theory to respond. The deeper implication is that cosmic history may have been more compressed at the start than familiar galaxy evolution suggests. Later galaxies often grow through long cycles of gas inflow, star formation, feedback, merger, and enrichment. In the first dense environments, those cycles may have overlapped tightly. A burst of massive stars could brighten the galaxy, enrich the gas, affect dust formation, and ionize nearby hydrogen in a short interval. A central black hole could feed during the same phase, adding compact light and energetic radiation. Fresh gas could keep flowing inward from the surrounding web of matter. In a small system, these processes would not be isolated chapters. They would influence one another directly. That may be the main lesson Webb is beginning to teach. Cosmic dawn may not be understood well by stretching later galaxy behavior backward. It may require its own physics of scale, density, composition, and feedback, still grounded in known laws but arranged in conditions that no longer exist in the same form. The troubling quality of Webb's findings lies in this demand for a new level of precision. The telescope has not offered a single impossible object that can be explained away and forgotten. It has opened a region where many measurements point toward accelerated development. Brightness asks for efficient light production. Compactness asks for dense early assembly. Chemistry asks for previous stellar generations. Hydrogen transparency asks for strong escaping radiation. Little red dots ask for early black hole activity or unusual stellar systems. Dark matter hollows ask whether the invisible scaffolding formed deep enough wells soon enough. Each issue touches the others. Changing one part of the model affects the rest. A faster first generation of stars helps with enrichment and brightness, but changes feedback and reionization. More active black holes help with compact luminosity, but demand faster black hole growth. Earlier dense halos help gather gas, but must remain consistent with the large-scale structure measured elsewhere. The new picture must satisfy all these constraints at once. That is the real challenge. The final view is not one of collapse, but of refinement under pressure. Science becomes strongest when new instruments expose where a working model is incomplete. Webb has done that at the edge of observable time. It has turned cosmic dawn from a mostly theoretical interval into a landscape of measured galaxies, spectra, redshifts, colours, emission lines, and unresolved engines of light. The young universe now appears active earlier than expected, not because it was magical or lawless, but because the first conditions may have allowed matter to gather, shine, enrich, and clear its surroundings with surprising speed. The older slow sunrise has not vanished entirely. Many galaxies surely formed gradually, and much of the universe remained dark and neutral for a long time. But Webb has shown that the first visible lights included compact regions of remarkable activity, and those regions may have shaped the later universe sooner than anticipated. At the current edge of observation, the beginning looks less empty and less delayed. It looks like a place where the main ingredients of galaxies were already interacting, where stars, gas, chemistry, radiation, gravity, and black holes began their work together in a compressed and uneven dawn. The evidence now rests in a quieter place. Webb has not ended the story of the early universe. It has made the first visible chapters more detailed, more demanding, and more alive with structure than they once appeared. The distant galaxies remain faint in the data, but the questions attached to them are large. Their light carries distance, age, chemistry, motion, and uncertainty together, and each measurement turns a little more of cosmic dawn from theory into something that can be tested. Some early sources will be revised as better spectra arrive. Some will become less extreme. Others may grow more important as their distances and features become clearer. That is the natural rhythm of discovery at the edge of observation. The first view is never the final one. What remains is the sense of a young universe that did not wait as long as expected to begin its work. Gas gathered, stars formed, heavy elements appeared, radiation opened paths through neutral hydrogen. Compact engines of light may have fed inside the first small galaxies. None of this requires the universe to be broken. It requires the beginning to be understood with greater care. The old slow sunrise gives way to something more uneven. Dark regions still waiting, bright regions advancing early, and the first structures shaping their surroundings while the cosmos was still young. Webb continues to collect the ancient light, not as an answer already complete, but as a set of traces from a time that can never be visited directly. In those traces, the early universe becomes less empty and more intricate, less silent and more active, less simple than the older outline allowed. The mystery is calmer now, but not smaller. It has firmer edges, better measurements, and a longer road ahead.